Walaikum assalam, Fahad. This is audible to you both? Fahad and Reem.
Yes, ma'am.
So in the last class, we had started with continuous charge distribution. So what is meant by continuous charge distribution is distribution of charge, be it length, be it on surface area, be it inside the volume. This is what is meant by students' couplet. All right. So three types of charge distributions we had studied. One was linear charge distribution, where charge is distributed all over the length. So we get linear charge density. This is known as lambda. We represent it through lambda, which is charge per unit length. Then we had seen surface charge density. Surface charge distribution means charge distributed over the surface. So surface charge distribution is what? This is charge per unit surface. That is the surface area. And then finally, we had the volumic charge distribution, in which the charge is distributed in the volume, means inside the container, in the volume of it. And the volume charge density, this is given by charge per unit volume. So till here we had discussed it. So any doubts till now before moving on? Just go through it once. Any doubt, just text me or ask me directly. Then we'll see different materials. Some have fixed electric fields that we'll discuss. So this is electric field due to infinite line or charge or wire, you can say directly, or rod even, you can say, if you get any among these. Basically, if you have a wire or a conductor in this manner. So let's say you have a wire with you. Fine. Now this wire has certain charge around itself. The linear charge density is lambda. And what is meant by linear charge density? Madiha, just now we have revised. I think you must be remembering it now. Madiha, what is linear charge density?
The charge which is present in one-dimensional field.
That is length, charge per unit length. Simply say in this manner, charge divided by length or charge per unit length. Okay, good. All right, so let's say this is infinitely long, means the ends, these are reaching plus infinity to minus infinity. There's a wire. Now, because it's obviously not possible is to calculate for the whole infinite length. So what we'll do, instead of calculating it for the whole infinite length, we'll just take a portion of it. But we will assume that it is infinitely long. Now, what did I tell you for Gauss' law? Okay, Reem, you tell us, what was Gauss' theorem? In the last class we have did it. What was Gauss' theorem?
It was the total flux through any closed surface.
Through any closed surface. This is given by as
1 by
epsilon naught times the what?
Total charge enclosed.
Total charge enclosed. Good. So it's within a closed surface, but this is an open wire. Q by epsilon naught. Good. But this is an open wire. So what do we have to do? We have to construct a Gaussian surface. Whenever you have a wire, or a line, Gaussian surface is always cylindrical. If I draw a cylinder around it in this manner, see, now talking about the cylinder, is this a closed surface now? Is my charge inside my wire inside a closed surface? Now I can say Gauss theorem will be considered. So consider an infinite long wire whose lambda is what? This is linear charge density. This is what? This is linear charge density. Linear charge density means charge per unit length. Now let's take few criterias also. Let's say this is the separation of the edge of the cylinder with the wire. We are assuming that it is an infinity because we are considering if we have an infinitely long wire or if we have an infinitely long sheet. So sheet we'll do after this. But if you have an infinitely long wire, how will you get the electric field? So this is a part of your syllabus. You have to remember this. Whatever conclusion we'll get, no, derivation also along with the final answer, that you have to remember, because in the questions it will be directly given electric, what is the electric field for an infinitely long wire or an infinitely line rod is placed in somewhere. In this manner your questions will be given. So you should be prepared for this case, electric field due to infinite line or electric field due to infinitely plane sheet. So plane sheet we'll do. Right now we are just focusing on electric field due to this wire. And infinite casely we are taken. See, if it's not an infinity case, you can just take, you know how to solve it. For a line you already know how to solve it, but what if it's infinite, how can you calculate? So let's take r is what? R is the radius. R is the radius of Gaussian surface. R is the radian of Gaussian surface. Now these are positive charges, so what will be directions of electric field? For positive charges electric field are away, and for this side of wire electric field lines, this will be in this manner, moving away from the charge. In this manner you will be having the electric fields. So you have the electric fields in this way. Now we know the radius of it. Let's say the length of this is L. Let's also assume a length. Let's say the length is L. So L is the length of the Gaussian surface, and Gaussian surface is the cylinder. Now listen it carefully. You have three surfaces with you. First one is this surface, second one is this surface, and third one is this surface. Two are the flat surfaces, these two flat surfaces of the cylinder. One is the curved surface around it. Now the curved surface is there and two flat surfaces. If I tell you what will be the direction of area vector, Rifat, tell us what is the direction of area vector of this. Area vector is a perpendicular drawn. So if I draw a perpendicular, which direction will it lead to? Upwards, downwards, right, left? Rifat, just try, I'll help you. Just draw a perpendicular and see in which direction it is leading. Rifat, if you draw a perpendicular here, will it be pointing in this manner, upwards, downwards, right, left? Upwards. So yes, Fahad, your answer was right. It will point towards upwards in this manner. And electric field is where? Electric field is moving in this direction. So Fahad, tell me what will be the angle between the area vector and electric field? 90 degrees. Good. So for the first surface, flux through the first surface, this will be E S cos 90 degrees, and cos 90 is 0. So we get flux through this curved surface is 0. Now flux through this bottom surface, second surface. See, now Rifat, tell us where will the area vector lead us? Downwards, upwards, Rifat? In this manner. If you draw a perpendicular, downwards, good. It will be downwards. And electric field is in this manner. This is the area vector. Again, it is making an angle of 90 degree. So flux due to the curved surface, this is ES cos 90. This is again 0. Now we are left with only the third surface. We have to calculate the flux through the third surface. All right. Now, flux through the third surface will be what? It will have some value. How can you say? Now, check for the angle between area vector and electric field. If I draw a perpendicular on this surface, it will be in this direction. This will be the area vector, and this is the direction of electric field. Electric field, area vector, both are in the same direction. What is the angle between electric field and area vector? Look at it. What is the angle? If both of them are in the same angle, in the same direction? Not 180 degrees. See. 0 degree, 0. Good, Madhya. It is 0. See, if it had been, yes, it is 0. Had it been in this manner, then it would have been 180 degree. Both are pointing in same direction, so the angle is 0. So it is ES cos 0. Now, surface area is what? Surface area is 2 pi RL for a cylinder. This is the surface area for a cylinder. This you should already know. So flux will be what? Flux will be E 2 pi RL. So total flux, if I calculate, it will be phi 1 plus phi 2 plus phi 3, all the three flux. So this is 0, this is 0, this is E 2 pi RL. So the flux, total flux that I am getting, this is total flux phi, this is 2 pi RL. One thing. Now, what was Gauss theorem's formula? Fahad, you tell us, you had told me in the starting of the class. What was it? Q by epsilon naught. Good. So also we know that flux is what? Flux is charge enclosed divided by epsilon naught. This is through Gauss theorem. This is through Gauss law. Now, charge, if I tell you, if this is the charge is Q, lambda is the linear charge density, L is the length of this wire. Reem, tell us what will be the value of lambda, linear charge density? Yes, Reem? Lambda?
It will be equal.
Lambda will be equal to what?
So, to the length.
Only the length. Check in your notes. See where you had written for continuous charge distribution. You must have written linear charge density lambda, which is equal to what? Just check it. You will be able to remember it now. Found?
To charge and length.
Charge divided by length. Okay.
Yeah.
So linear charge density, this is charge divided by length. So lambda is charge divided by length. So Q will be what? Q will be equal to lambda multiplied by length. So put it here. Phi is what? Instead of charge, I will write lambda L divided by epsilon naught. So I have two values of flux. One is this one, and the other one is this one. Both the flux are same, both are for the cylinder only. I can equate them. This was E 2 pi RL, and this is lambda L divided by epsilon naught. Length cancels the length. Electric field is what? Electric field is lambda divided by 2 pi epsilon naught R. This is the value of electric field for a line, infinitely long wire or line charge. So if you see, electric field is inversely proportional to R from this formula. If you draw electric field versus R, it will be in this manner. All right, we'll do a question on this, but before that, note down the things first. Linear charge density, even if you do not write it, we are just adding it because you should know what will be electric field in terms of linear charge density. You can get the answer directly from here as well. Q by epsilon naught also. We are just replacing it because linear charge density is also involved in many of your calculations. So if it comes, how will you write? Just in case in your question comes, you should remember this formula, lambda by 2 pi epsilon naught small r. All right. So note down the derivation from here. We'll do a question also. 1 by 2 pi epsilon naught lambda by r. Yes, that's the same. It can also be written in that manner. 1 by 2 pi epsilon naught lambda by 1 by 2 pi epsilon naught and then lambda by r. Yes, yes. Or you can do one more thing. You can multiply it up by 2, up and down. So it will be what? It will be 2 lambda divided by 4 pi epsilon naught r, and 1 over 4 pi epsilon naught is what? The constant that you write. So which you can write it as 2k lambda by r. In this manner also you can. Both of them are correct. See, this is a question given. It says calculate electric field at point O. This is point O. So, what is the direction of electric field for positive charges? Away from the charge or towards the charge?
Away.
Away. Good. It is away. Yes, sir. It is away. So if I take this point O, which we have to calculate, at this point O, electric field away, if I draw this towards it, this will be wrong because it is positive charge. So because of the positive charge, it will be in this manner. And what about the negative charge? Towards or away?
Towards.
Towards. Good. So this will be the direction of electric field for the negative charge. So both of the electric fields are pointing in the right hand side. So net electric field will be what? Net electric field will be E1. Let's say this is E1 and this is E2. E1 plus E2. So electric field 1, we know, let me just make this as infinite so that it becomes clear that this is an infinitely long wire. So electric field due to infinitely long wire, we have just seen lambda divided by 2 pi epsilon naught r. If this is the point, this is the line, the separation between the point and the line is what? This is the point O, and this is the line where charge is distributed. What is the separation between O and this line? Wire and point O. Look at the separation is given to you.
D.
D. Yes, it is D. This is the separation, no? So it will be lambda divided by 2 pi epsilon naught D instead of R. Similarly, for E2 also the separation is D. This will be lambda by 2 pi epsilon naught D. Now add them. This is lambda by 2 epsilon naught D. This is basically we are adding it twice. This will be 2 by lambda epsilon 2 pi epsilon naught D. So 2 gets cancelled. Electric field will be lambda by pi epsilon naught D. All right, note it down. Then we'll do electric field for the plane sheet. We are not moving the line away. we have to calculate, let's say this was the point O. So we have, if I move in this manner, that will lead me towards the charge. But we know it is a positive charge. So that's why I'm drawing it in this manner. This is a negative charge. So if I draw myself in this manner, that will lead to towards the charge. If I draw myself in this manner, this will lead to away from the charge. So for both of them, the electric field is pointing in the same direction. That's why we can add them. Just text me done all of you when you all have written so that we can start the next topic. The infinite plane sheet is there. It means a sheet is there which is extending from minus infinity to plus infinity. Means it is everywhere. Infinitely long sheet you have. So obviously again it's not possible to calculate the electric field of the whole sheet. So we'll take a portion of it. Let's tear it from the middle and take a small portion of it in this manner. We have taken the portion of sheet, otherwise it was extending from infinity. So this is having certain charge, and now we'll not consider linear charge density. We have to consider surface charge density because it is plane sheet. 2 dimensions have been involved. Now the Gaussian surface that you will take. Since line can be enclosed in a long line, you can enclose in a long cylinder, but cylinder you can never enclose a sheet into the cylinder. So what you can do, if you put the cylinder in this manner, piercing through the sheet in this manner, so now this will be your Gaussian surface. So again you have 3 surfaces. This is the first surface, this is the second surface, and this is the third surface. Electric field, because of this plane sheet, it will be moving in this manner because it's a plane sheet and it has positive charges, so it will be away from the sheet. Away from the sheet will lead you in this right hand side direction. This is the direction of electric field. Now let's check for each of the surfaces. Reem, you tell us, for the first surface, where will be the direction of area vector? This surface.
Right side.
Right side, very good. It will be in the right side. So are we still getting 0 because of the flat surface? Will the flux will still be 0? What is the angle between area vector and electric field now? Yes, class? Electric field and area vector are pointing in the same direction. Fahad? Yes, Matia, good. It will be 0. It will be 0 degree. So it will still not be 0. It will be having certain values. So flux will be something. ES cos 0 degree, which is ES. Flux due to the second surface. See, it will be in this manner, left hand side. Electric field and area vector. So electric field because of that surface. See, it's a plane sheet. Positive charges will be here and positive charges will be here. So for the first surface, we considered the electric field in this manner. So we got it 0. For the second surface, means this surface electric field will be in this manner. So again, electric field and area vector both are making an angle of 0 degree. So flux due to the second surface will also be ES. Talking about this curved surface, if I drop an area vector, now tell me what is the angle between area vector and electric field?
90.
90 degrees. So this will be 0. This time this curved surface is giving us no electric field. So this is cos 90, which is 0. So total flux will be what? Total flux. It will be phi 1 plus phi 2 plus phi 3 flux due to all the surfaces. So phi 1 was ES, phi 2 was ES, and this was 0. So total flux we have it as 2ES. This is it. Now, according to Gauss theorem gives you flux. According to Gauss theorem, it will be Q by epsilon naught. Now Madiha, you tell us what will be the surface charge density? Sigma. Yes, Madiha. Surface charge density, even if you're forgetting, look into your notes in the last topic we have did. Continuous charge distribution. Yes, Madiha? Surface charge density. It's what? You're not able to unmute. Others, please check. Are you able to unmute?
Yes, ma'am.
Yes, you are able. Okay, connection issues. Okay, fine. So you type the answer, Madiha. You type, I'll read it. It's okay. No need to unmute. There must be some connectivity issues because others are able to. It is Q by A. Good. Q by A means charge per unit area. So charge is this, let's say the surface area is S. Now charge will be what? Sigma multiplied by, you can use it in this manner, but most of the questions you get in terms of sigma. Most of the questions. So you have to remember it till sigma also. Sigma S. So phi will be what? Charge, you have sigma S divided by epsilon naught. Now let's equate 2ES with this. This is a very important. This is used in your second chapter. This will be utilized throughout. I told you in the last class only, continuous charge distribution. This is utilized in your whole 12th standard. This was what? 2 times ES. So see, surface area gets cancelled. Electric field is what? This is sigma by 2 epsilon naught. Rifat, tell me one thing. How will electric field vary with R now? I'll help you. Just unmute yourself and try. See, if there is any R in the formula, do you see any R in the formula, in this final formula? Rifat? No. So it means, will electric field depend on R?
No.
No. So it means if anyone asks you, how does electric field depend on R in case of plane sheet? You simply say it is independent of R. All right. That will be your answer because you're not getting any value of it. So if you plot the graph of it, it will be somewhat like this. This will be electric field. This will be R. Since it is not depending on the position, it will be a straight line. Independent of the position. Now, I'll not discuss any numerical on it, but I'll tell you how do questions come from, and that will comprise all your numericals and everything that comes from this question. But before that, I want you to write till here. If you have any doubts, you can clarify. Then we'll understand how do questions come from this one. This derivation was easier than the previous one. Yes, Fahad, because both the surface area vector and the electric field, those are in the same direction. So that's why you're getting cos 0. And cos 0 is 1. So that's why we are getting E multiplied by S. All right. So these are two sheets given to you. Most of the questions will be dealing with two sheets. For single sheet, you know, the formula is sigma by 2 epsilon naught. So that is easy. But maximum questions that you get involve two sheets. So I'll just tell you how to solve it, because otherwise you'll get direct formula based questions in this. If it see, the questions that comes from this portion is that it will give you 2 sheets, and in these 3 regions, out of all these 3 regions, it can ask you to calculate the electric field in any of them. For example, if we calculate the electric field in the first region due to this sheet and due to this sheet, Fahad, you tell me, what will be the direction, left or right, of the electric field due to this sheet? Left. Good. Very good. This will be in this manner. Why? This will be even. Let's say this is first sheet, this is second sheet. Because we have to move away from this. Fahad, you only tell us, for because of this second sheet, what will be the direction, left or right? Be right. Very good. Quickly he responds. This will be E2. These are the directions of electric field. E1, see, E net, what will you get? This will be E1 plus E2 in vector forms. E1 is what? E1 is electric field due to this positively charged sheet. And the general formula of electric field is sigma by 2 epsilon naught for a plane sheet. This we have already studied. So this will be sigma 1 by 2 epsilon naught in this manner. Now, these are 2 different electric fields. Both of them are not having the same surface charge densities. One is sigma 1, other one is sigma 2, means the electric fields are different. So, for the negative x-axis, what is the unit vector, Rifat? Yes, Rifat, unit vector. Do you remember? I cap, j cap, k cap, minus I cap, minus j cap, minus k cap.
I cap.
Minus I cap. It won't be I cap. See, for x axis, remember I cap. For j axis, for y axis, remember j cap. And for z axis, remember k cap. If it is positive, then add plus. If the axes are negative, then add minus. See, this is negative x axis, so it will become minus I cap. Clear, Rifat?
Yes, ma'am.
Good. So this will be minus I cap. Then E2. E2 is because of this. This will be sigma 2 divided by 2 epsilon naught, and the direction is positive x-axis. So this will be I cap. This will be your answer. Whatever values are, you can write. Otherwise, question will be in this manner. Second portion. So Fahad gave the previous direction. No, Madhya, let's hear from you. Direction of electric field at this point because of first sheet, left or right?
Right.
Right. It will be right because we have to move away. Good, Madhya. This is E1. And Madhya, you tell us because of this.
Left.
Just check once again, why left?
Will it be right now?
It will again be right. Where, Fahad? E1 in place of E2. This is E1 only. Electric field due to this sheet. This is the first sheet. So this is E1. All right. Yes, Madhya, what did you answer? Right only. Because it's a negative sheet. Negative. Negative we move towards. Don't ever think that one is here, so other one will be in this manner. Just go by the logic. So E2 will also be in this direction. Both of them are pointing to the same. Now is this clear, Fahad? This was E2, which was missing, which you thought I was writing. Both of them are pointing in the same direction. So now again, E net electric field that you get, it is E1 plus E2. So this is what? E1 plus E2. This is E1 will be sigma 1 by epsilon naught. En will be sigma 1 by 2 epsilon naught. This will be I cap because this is pointing in right hand side. And this will be sigma 2 by 2 epsilon naught, again pointing in I cap. Now third region. Let's take this region. Reem, you tell us the directions for E1 and E2 at this third point.
Left.
For E1 or E2?
E2.
E2 it will be left. Good. For E2 it will. And for E1?
It will be right.
It will be right because we are moving away from the charge. So E resultant will be what? It will be E1 plus E2. E resultant will be C. E1 is again sigma 1 by 2 epsilon naught. E1 is in this direction, that is positive x-axis. So this is I cap plus sigma 2 by 2 epsilon naught. This will be negative x-axis minus. All right. So note it down. In this manner, you get the question. Any region can come in your paper. Or the sign of the sheets can get changed. For example, one I have taken as positive, other as negative. No, it can happen. You can get both the sheets as positive, both the sheets negative. The concept remains the same. First, find the direction of electric field, write down the formula of it and the unit vector in this manner. If any question, different question comes. And I've written as the net electric field. You can write it anyway. Net electric field. ER I've written as the resultant. So it's basically the net that we get. Or one place I've written E. Anyway, any manner you can write. But just remember, this is the net total electric field of the system. And what about others? Done?
Yes, ma'am.
Yes, ma'am.
Now, all the questions that you will be getting, or the section that is left in your chapter, is regarding the spheres. So, before going into the derivation of spheres, so just understand what are kinds of sphere available. Majorly, you have one kind of sphere where the charges reside outside. The other kind of spheres have charges within them. One is this case, other one is this case. Now, what kind of charges, what kind of spheres have charges residing? One is a hollow conducting, means there is nothing inside the sphere and it is conducting. It's a conductor. It allows electricity to pass. In case of conductors, electrons reside on the surface of it. This is hollow conducting, or it can be hollow non-conducting. Conductors are those substances which allow electrons to pass through them. Non-conducting, or it can be solid but conducting. And the other case you have as the solid non-conducting. Only the solid non-conducting spheres have charges within them. So this is now not a part of your syllabus. You will just do the derivation for these cases. So let's start with hollow conducting, hollow non-conducting, or solid conducting. So you have in your syllabus now, earlier that was included, now it has been deleted. This is electric field due to, but in your entrances that also come. Solid non-conducting one. Electric field due to hollow conducting or non-conducting or solid conducting sphere. So all these have the same answer. That's why I'm writing the heading together. No need to do it separately. You also remember the same answer. Any of these cases come, you can write the derivation. But see, there are three cases also in this. One is what? See, if I say this is a sphere, if I tell you this is a sphere, one, you can get the electric field. See where all the places where you can get the electric field. One, outside. Here you can get a point to calculate the electric field. Other point can be on the surface to calculate the electric field. And the third point can be inside anywhere to calculate the electric field. So we'll be dealing with these three cases. So this is the last portion of your chapter. So understand it carefully. So let's start with the first outside portion. Case 1 is when electric field outside the sphere. First case we are taking. These three cases are there. First we'll deal with the first case. Now, if the point is lying outside, it means I have to enclose this point. If it was inside the sphere or on the surface, then there was no need of any Gaussian surface. Now I have to draw a Gaussian surface. It means if I tell you this is my sphere, this is the sphere and radius of sphere is capital R. And this is a sphere with charges residing outside. Now I have taken some point. So I have to draw in a Gaussian surface to enclose it. For example, this was the point I had taken. Now I have to take the separation from the center of the sphere to this as the Gaussian surface. This is your Gaussian surface. Now you can see all your charges are residing inside the Gaussian surface. That's why there's a need of Gaussian surface. Gaussian surface is any surface that encloses your charge, required to enclose your charge. So this is the Gaussian surface and this is the radius of it. Again, it's a positive charge. Let's take an aspect of it. Let's take this portion, or let's take it. Because of the positive charge, electric field will be in this manner. And if you take any portion, the surface area will also be in this manner, area vector, and both of these are lying parallel to each other, making an angle of 90 degrees. So see, what will be the electric flux? Flux will be again Es cos theta. Cos theta is 0 degrees. So flux is Es. What is the surface area of a sphere? Do you remember surface area of a sphere? Anyone who remembers the surface area of sphere? If R, capital R is the radius, then surface area is 4 pi r square. If I asked you the volume, then it would have been 4 by 3 pi r. That is the volume of a sphere. Surface area is what? 4 pi r square. So phi is what? Phi will be E 4 pi capital R square. This will be what? Electric field. Now, flux is, I've got one flux. What is the second step? What we always do? We write the Gauss theorem. Gauss theorem, this is what? This is Q divided by epsilon naught. This is the charge that I get. Now let's equate it at this step only. At the last, we can write the surface charge density. Electric field, it was what? E 2 pi 4 pi r. This was E 4 pi r square. Okay, one more thing. In this, we won't be writing capital R square. I'll tell you. Just one mistake I've done while writing. See, we are taking the Gaussian surface now. So we have to write the surface area of the Gaussian surface. We are not writing the surface area of the smaller sphere. Why? Because we are considering the Gaussian surface. Now this is where you have to do your calculations. This is your system now. So radius will also be taken off the Gaussian surface. Small r is the radius of the Gaussian surface and capital R is the radius of the sphere. So we'll be writing 4 pi small r square, not capital R square. Is this clear? Why am I writing small r square to all of you? Or should I repeat? Is this clear?
Ma'am, can you repeat?
I'll repeat. See. There are two surfaces. One is your Gaussian surface, means this. So small r is the radius of Gaussian surface. Other one is your capital R. This is the radius of the sphere. Now, charges are residing on this sphere. But these, if I do not draw this Gaussian surface, where will the charges be? Charges are outside. They are not enclosed. So it means I need to draw a Gaussian surface. Why do I need to draw a Gaussian surface? I need to draw to enclose it. Enclose all the charges in this manner. That's why I've drawn it. Now, this acts as Q enclosed. Just imagine this is your sphere with small radius r and this is acting as Q enclosed. This hole is acting as Q enclosed, charge enclosed. So radius will also be considered of the Gaussian surface. Why will I consider the radius of the sphere when this is not my Gaussian surface? This is my system right now. So I have to consider this as the system. So the surface area will also be considered of it. And its surface area is always given by 4 pi r square. So radius of the Gaussian surface will be taken. Is this clear now, Reem?
Yes, ma'am. Thank you.
All right. So we have electric field and let's equate it to Q by epsilon naught. This we have done. So electric field is what? This is Q by 4 pi epsilon naught r square. This you are getting. Now let's substitute charge. Surface charge density is what? Charge per unit area. Now surface charge density. Now listen to this carefully. Surface charge density is what? Charge per unit area. Means on the area wherever charge has been distributed. So Reem, tell me, is the charge distributed on the sphere or on the whole Gaussian surface? Reem?
On the sphere.
on the sphere. That's why when we are just writing the surface charge density, no, we'll write charge per unit area. Now this time we'll consider, because there's no concept of Gaussian surface in your surface charge density. In the last class also we did it. So this will be what? Charge will be sigma 4 pi capital R square. Put it. Electric field is sigma 4 pi capital R square divided by 4 pi epsilon naught small r square. 4 pi gets cancelled. Electric field, this is sigma capital R square epsilon naught small r square. This is your electric field. So the third and the fourth. Okay, which portion? The whole one, Fahad, or the specific topic? Okay, this I'll explain you. See, Fahad. This was your point. Electric area vector is pointing right hand side. Electric field is pointing right hand side because electric field lines are away for a point charge. So we wrote ES. Surface area for this Gaussian surface is what? 4 pi small r square, because the radius of this Gaussian surface is this small r. Small is the r is the radius of it. So when you put it, it is E 4 pi small r square. Also, phi is equal to q by epsilon naught. From where? This is from your Gauss theorem. This is from your Gauss law. So when you equate both of them, you get q by 4 pi epsilon naught r square. Now sigma, surface charge density, is what? Charge distributed on the sphere. Means charge distributed on the surface area of the sphere. That becomes q divided by 4 pi capital R square. So from here you have the charge as sigma 4 pi capital R square. Put it in this value, you finally get sigma capital R square divided by epsilon naught small r square. Clear? Note down this, then we'll do the third and the fourth case. Not third, fourth case, second and third case. Electric field on the surface and electric field inside it. See, now the second case is electric field on the surface of sphere. It means my point is where? My point is lying here only on the surface. So where will the Gaussian surface be? The Gaussian surface will also be coinciding with this. If I draw the Gaussian surface, this will be the Gaussian surface only. The radius of the Gaussian surface will be small r if I want to calculate. So can you see capital R and small r both are equal now? Why? Because my point is lying on the surface. So both the radii, they become equal. Now again, if I take electric field, if I take area vector, both are same. So electric flux will be E S cos 0 degree. Flux will be E S. Now the surface area. See, now the surface area for the Gaussian surface and the sphere both are same. So now I can take it as 4 pi capital R square. We always take Gaussian surface, Fahad, because we have to enclose the charge. The reason is that we always have to enclose the charge. That was a condition and property of Gauss theorem, if you remember. Okay, this is 4 pi r square. So phi is what? This is E 4 pi r square. Flux is what? Q by epsilon naught. Q by epsilon naught from where? This has come from the Gauss law. So electric field, equate both of them. This will be 4 pi r square E is equal to Q by epsilon naught. So electric field is equal to Q by 4 pi capital R square epsilon naught in this manner. This is, you're getting the same answer here. Difference in the answer is R. There you were getting small r. Here you have the radius of the sphere. Now, if you write the surface charge density, it will be Q by A. That is the surface area. Q will be equal to sigma 4 pi r square. Put it. See what's your answer you're getting. E will be equal to Q is sigma 4 pi capital R square divided by, this is what? 4 pi capital R square epsilon naught. 4 pi R square cancels 4 pi epsilon naught. You get sigma by epsilon naught. Why are we getting a different answer? Because here the radius, here is the difference. We are considering now the radius of the sphere. In the previous case, we were considering area, surface, this radius of the Gaussian surface. Since Gaussian surface and spheres are overlapping, we can consider this. Now the third case is the easiest. Third case is the best. When the point lies inside. If you have a sphere with you, sphere will be having charges outside. Can you tell me, in this sphere, is there any charge inside the sphere? Yes or no? No.
No.
No charge is there. Exactly. It means your Q enclosed is 0. So flux will be what? Flux will also be 0. Electric field will also be 0 inside. If I give you this point, even if you draw a Gaussian surface, there isn't any charge. Since there is no charge, the net electric flux, it will be 0. So see, we have done 3 cases. Let me summarize it for you. With the help of a graph, I'll summarize. That will become easier. Just a second. This is what? This is electric field and this is separation of the Gaussian surface, small r, the radius I've taken. Now, this is the center point where r is equal to 0. R is equal to 0 means what? Radius is 0, means at the center of the sphere. This is at the center of the sphere. Now, this point I have taken at the surface. So at the surface, small r is equal to the capital R, means the radius of the Gaussian surface. This is equal to the radius of the sphere itself. So small r is equal to capital R. This is what? This is the surface of it. Now, from the center of the sphere to the surface, all the space that we get, we call it as inside, means where small r is less than capital R. This is what? This is inside the sphere. Center inside, then at the surface. And any point beyond surface is what? That is outside, where your Gaussian surface radius is greater than the radius of sphere. This point is taken as point outside. Now if we plot a graph, see, for the first case, means inside case, inside electric field is what? Electric field is 0. So we have no value of electric field. Means on the graph we have baseline. This is just coinciding with x. When you draw it, draw it with the help of scale so that it coincides, because electric field is 0. Now electric field at the surface. See, electric field at the surface. This is sigma by epsilon naught. Means independent of the sphere. So this will be, it will be having certain value. This is sigma by epsilon naught. Now outside the first case which we did, this was the first case. See, the variation of electric field with small r, it is inversely proportional to small r. So electric field will be what? Electric field will be inversely proportional to square r square. Inversely proportional to r square. Here it is independent and here it is 0. This is the summary of this first. All right, so quickly note it down. Wherever you are not able to understand, ask me. I'll repeat that point. While noting, you might get stuck. These are the 3 cases. And that finishes off your first chapter also. So revise this chapter properly, especially all those students who are having their UTs next week. We'll start with the next chapter. So if your test is on 22nd, then we'll have one class on potential already. And whatever doubts you are having from the second chapter, you can ask me in the next class. So we'll do it in detail, otherwise don't worry. See, in this, r is equal to 0 is at the center, r is equal to capital R is the surface. Any point within the center and the surface in between is inside, and any point above the surface, that is outside. Now, how do we plot the graph? First, we are plotting it from center to the surface, means inside. So inside electric field is 0. So 0 is at the origin. That's why we have just traced it. Then at the surface, there is no value of electric field depending on small r. Electric field value was sigma divided by epsilon naught. This was sigma by epsilon naught. That was the value at the surface. This one. Now after it, which point will be there in the surface, above the surface? Outside point. And we had seen electric field varies inversely proportional to r. So whenever there is inversely proportionality, we draw a graph in this manner. Now clear, father? Any doubt in still this part? Just ask me. Case 3, which case 3? Inside is this case 3. This is inside, 0. This is case 2. And this is case 1. No. Actually, Fahad, this is clear. Just trace it on this axis only. If you trace it on this axis, then you will be able to understand. Actually, I was just tracing it, so it's not above it. All right, draw it inside it. Just write done when you all have plotted the graph. Others done? Only Fahad and Reem have told. Madiha and Rifat done? Okay, Rifat has also done. What about Madiha? Still doing? Okay, so whoever have written it, you can leave the meeting. We'll continue the second chapter in the next class. Only Zaid and Wafia, you stay. Rest of them, you can leave the meeting now.
Thank you, ma'am. Fahad, you'll have the extra classes in the month of July only because of your summer vacation. So then I'll inform you. Let's get over with June 1st, then I'll inform you. I'll arrange the classes. Rifat and Madi, if you're done, you can leave. I have a class with Zaid and Wafia. Yes, hello Zaid and Wafia. Is this audible to you both?
Yes, sir.
Yes, Zaid Ahmed. Your mic is not working, I guess. No, I'm still not able to hear. No, Zaid, you're not audible. Am I audible to you? Are you able to hear me, Zaid? All right, there must be then connectivity or network issues. It's okay, Zed. Whenever you have to ask something, or if I ask you, you can simply type it for today. It was working yesterday. All right, I think it must be network issues. You can, it's okay, it's okay. For today's class, we have a short class only today. So you can type everything if you get any doubt or in between. Same with Wafia. Now, see, basically, in your first chapter, this is a huge chapter. You already know your first chapter of class 11th, electrostatics. That is your electric charges and field. So, in the next class of this batch, we have completed this chapter in today's class. This was the last class of this chapter. So, what we can do is that we can, after the classes at this time, slowly we can have half an hour classes and complete the backup of this chapter. That won't take so much of time. You can have the backup of this. What you can do is that in today's class, if we study electric field, this is the important topic for your second chapter, then only you will be able to understand electric potential and capacitance. So that's why I'm starting with electric field today only, so that you're able to cope up in the next class. If we do this chapter, no, electric field topic from this chapter, then you won't be having so much difficulties, because electric field will be constantly utilized in your electric potential and capacitance. So from the next class, new chapter will begin, so you will be able to understand. Good. So see, before the concept of electric field, I'll tell you what is meant by electric charge. Briefly, I'll discuss methods of charging, quantization of charge, that I'm not dealing today. That we'll have a separate class for